Okay, then we will start today's lecture. So in the previous lecture, we proved the duality. So let's review just the notation. So this mu sub nk is the mixed moment, but we can also define it as the generating function for Mochkin path from 0, 0, n, k, like that. And then we have the usual weight for the Mochkin path. And nu nk is basically the coefficient of the orthogonal polynomial, Pn, but we can also define it combinatorially using the Fabard tiling. So this means the Fabard tilings of size n with exactly k red monomials. So red monomino was for 1x, but in this weight prime, we only consider minus lambdas and minus b's. So x's are not counted as weight. And we proved that under these definitions, we have two types of dualities, like this and this right here. So we proved both combinatorially. And for the next few sections, we will consider some special cases of this. So the first, we will consider this. And so here we said bk is x sub k, but actually we are doing nothing. We just keep bk, but for some reason we will use indeterminate xk. So you can think of this as arbitrary, bk are arbitrary, but we put lambda k to be 0. So lambda k's are all 0, but bk's are arbitrary, but we will write bk as just xk. And then, so because lambda k equals 0, Mochkin path, if pi is in the Mochkin path, what happens? We go from 0, 0 to n, k. In the usual way, we can go up, horizontal, up, down, horizontal, or something like that. But because of this, we are not allowed to have down steps. We only have up steps and horizontal steps. So it's like, maybe I can up, horizontal, horizontal, up, horizontal, up, and horizontal. Let's say we are somewhere here. So nk is here. Then there are only, only u and h steps, right? Because lambda step will just contribute 0, so you can ignore them. And the weight is if the weight of up step is always 1, so you can just forget about their weight. But here it's just bk, where k is the height. But now bk is xk, so we will put x1 here. The height is 1, so it's x1, x1, x2, x3, like that. So our Mochkin path looks like this, only up steps and horizontal. So we cannot go down. But let's see what this is. So this is n, this is k, but in fact, we cannot go we cannot go inside this region because, we have to go over here. You cannot go, because we have too few steps remaining. So in fact, what we can see from here is that this is n minus, so this is k, so this is n minus k, 0. Our path must be located inside this parallelogram, right? So because if we define, okay, let's say mu prime is just the up step 0, 1, just go straight up, then pi can be identified with, say, pi prime from 0, 0 to n minus k, k, where this is our pi, but we change up step using like u prime. So it's like you slant slant up step, change this into a straight up step, then we get a path like this. So up, horizontal, horizontal, up, horizontal, up, horizontal. So here, the weights are still the same, like that. So 0, 0, n minus k, k. Okay? And so, in other words, mu sub nk equals the path from, say, pi 0, 0, n minus k, k, weight of pi, where weight is just the product of xk, it's a different one, si for every horizontal step height I. Okay? But what is the weight, in fact? What is the weight of this path? Weight of pi is x1, let me write this way, x1, x1, x2, x3. So if you write the weight starting from the beginning, then the index of the weight, the index of the x is always increasing, weakly increasing, because it's basically the height. The height must be increasing each step. And notice that pi is determined by its weight. For instance, if I tell you the pi has weight this, then you can recover this, because this is the only way that you can make a path having this weight. In fact, this is because pi is determined by height of horizontal steps, right? Because this, the first one will tell you the height of the first horizontal step. This tells you the second horizontal step, and third and fourth. And once you know all the horizontal steps, then you can just complete the path by adding up steps in the appropriate positions. Okay, so this is completely determined, and every weight looks like this. So x, say we have n minus k horizontal steps, so there must be n minus k factor. So a1 x, I2 x I k n minus k, where what is the range for them? Weakly increasing. And what is the bound of the smallest one? 0. It may be 0, so it's 0. And what is the largest one? Largest possible? This is k, so it's k. So in other words, mu sub nk is a generating function for all such sequences. xi1 xi n minus k. Okay, this is what we showed. But this kind of sum is a well-known quantity called homogeneous symmetric function. So we're going to define homogeneous symmetric functions. But first, let me define what symmetric function is. So definition. Let's say x is a sequence of indeterminate. X1 is like infinite sequence, let's say. And a power series f of x0, x1, dot, dot, dot. So we have infinitely many indeterminate. So power series, so we may have an infinite sum. Could be finite, it's okay. A power series in the variables x0, x1, dot, dot, dot is called a symmetric function. A symmetric function if it is invariant under permuting variables. So if you permute the variables, then it may change, the polynomial or power series may change. Usually it must be changed. But if it has symmetric property, then it doesn't change. If that's the case, for any permutation of variables, it stays the same, then we call it a symmetric function. So for example, fx0, this is probably simplest one would be the sum of all of them, let's say. No matter how you permute the variables, the sum is still the same, so it's a symmetric function. It's a symmetric function. But if you define something like x0, x1 squared, let's say, it could be a polynomial. It's not symmetric. Because if you change x1 and if you permute x1, x0, this is not equal to x1, x0 squared. So it's not symmetric. Not a symmetric function. The symmetric function is something like that. And okay, so there are many important symmetric functions, but we will look at two of them. A homogeneous symmetric function or sometimes it's called complete homogeneous. Complete homogeneous, but yeah, just for brevity, let me just call it homogeneous symmetric function. But sometimes it's called complete homogeneous symmetric function. Is which h sub k, and yeah, let me just write this. Yeah, okay, sorry. In the variable, we have to specify the variables. In x0, x1, dot, dot, dot is something like this. hk for some k, a non-negative integer, sum over all k weekly increasing sequence of non-negative integers, xi1, dot, 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 xik. So in other words, you select k variables with repetitions allowed. Okay? Because they are all increased order, you don't consider how the order you choose the elements. Okay? So you just select k variables with possible repetitions, and then you add them all. That will be a homogeneous symmetric function. And an elementary symmetric function is similar. Of course, in the same variables is exactly the same. Except, of course, we use a different notation, E. And here we don't allow repetitions. So they must be all distinct. So you select k distinct variables and then you multiply them all. And then you add all possible ways of doing this. Okay? And in fact, if we consider only finite many variables, then they become polynomials. So in that case, we say a homogeneous symmetric polynomial is defined similarly. So it's really the same, except we have finitely many variables. It's exactly the same, but of course we have to have these conditions bounded by 0 n. So these are the very possible variables over here. And E is the same. And elementary symmetric polynomial is E, and delete all the equalities like that. Okay. But sometimes I'm not going to be very precise, and then sometimes I just call it a symmetric function, even if there are only finitely many variables. Okay. So examples. Oh, by the way, I'm gonna define. Also, we define h sub 0, e sub 0 to be 1, just for convention. And this is 0 if k is negative. Okay, this is just our convention. An example. What is h1 of 3 variables, x1, x2? h1 is the same as e1. And you just add, there is only one way to select x0 or x1 or x2. So this is it. What about h2? There are many ways. So you can select x0 twice, or x1 twice, or x2 twice, or you can select x0, x1, or x0, x2, or x1, x2. So this is a homogeneous symmetric function. What about E2? So, but we don't have this, right? Only we have the other terms. Because you cannot select something twice. And E3, x0, x1, x3, what is that? Oh, sorry, this is 2. There's only one way to select 3 variables, so it's going to be this. And what about E4? There is no way we can select 4 variables from 3 variables without repetition, so it's 0. But H4 is not 0. Okay. So these are the definitions. Quite simple. The symmetric functions are a very important topic in combinatorics and also algebra, like representation theory and things like that. But we will not go into the details. We only consider those basic things like this. And if we now we know the definition of the symmetric, homogeneous symmetric polynomials like this. If you look at this looks exactly like this homogeneous symmetric function, symmetric polynomial, right? There are n minus k variables to select, and this is the range for the variable, so x0 up to xk. So we can say that, so theorem is a summary, more or less. If bk equals xk and lambda k equals 0, then mu and k is the homogeneous symmetric function, x0, x1, xk. Okay, so in this case, we have a nice description. That's a simple single homogeneous symmetric function. And what about nu, the coefficient? And we have this is the end of the theorem. So nu nk is, we know that this is a generating function for all Favart tilings of size n with k red monomials, weight prime of t. And because lambda k equals 0, that means we cannot have a domino. We only have monomial, only squares. We have only squares, single squares. So only no dominoes. That means T has this only. All right. Maybe the example. Let's say T equals n equals 7, so 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. We only use red monomials or black monomials, but let me say that we choose these for red squares and the others for black squares, like that. And what is the weight? So we don't have weight for red things. For these we have b, but b is x, so it's x is minus x0, minus x2, minus x3, minus x5, like that. So what does that mean? For each of these square, we have two possibilities, either black or red. But if it's black, we put the weight minus x of that index, and like it. So here, weight is always, so weight minus 1 to the n minus k is the same because the number of red monomials is fixed to be k, and then the others have n minus k, so it's minus to the n minus k. These times something like xi1 dot 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 x I n minus, we still have n minus k axis, but what is their index? What are their index? The indices must be strictly increasing because we cannot have the same indices, right? So, and the smallest possible is x0, the largest possible is xn minus 1. So we have this. That means nu nk equals minus 1 to the n minus 1, they're all the same sign. 0, I1, but if you look at this, you realize it is an elementary symmetric function, right? This is minus 1 to the n minus 1, sorry, n minus k, e. So this number of variables that we choose is n minus k, and the range for the variables in variable indices is x0 up to xn minus 1. So we see also have this, okay? So let me write this, nu and k. So we have this and this. So let's say this is a theorem. We just prove this theorem, okay? And corollary is, we know there is a duality between this and this. So we can just apply that duality here. That gives us the following. So it's just so we have this matrix nk greater than 0 for this, and here we just put this matrix times minus 1 to n minus k e sub n minus k x0 dot 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 x n minus 1 is the identity. So again nk is greater than 0. And same thing holds, except we just change the order of the matrices. Yes, like that. This is also true. Okay. And because we have a matrix identities, we can also explicitly write n comma m entry of the product of the matrix, and that must be equal to delta nm. So we get another equation for this, the equivalent equation for this, and also a similar equivalent equation for this. And let me write one of them. One equivalent identity is this. Nm fixed greater than or equal to 0, fixed, and then summation k greater than 0 minus 1 to. I'm using the second identity. I'm just looking at n comma m entry of this product. Then that will be exactly this. X0 dot 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 xn minus 1 times h k minus m x0 dot 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 xm equals delta nm. We have identity like this. It's just equivalent. But let me rewrite this a little bit. So let's introduce another parameter n. Capital N equals n minus m. Suppose that this is greater than or equal to 0. Let's just consider this case, okay? Because otherwise it'll be 0. If this is, in order for this to be non-zero, n must be greater than or equal to k, k must be greater than or equal to k, so k is greater than or equal to m, so we only need to consider this case, otherwise it's going to be 0. So now let's rewrite this equation. Then k, capital N, a small n will be replaced by capital N, so n plus m minus k n plus m minus 1 times h k minus m capital N plus m comma m, right? And now let's replace k by m plus k. K must be greater than or equal to m anyway, so we can replace this by m plus k. I'm just rewriting the sum. Then k greater than or equal to 0 minus 1 to n and n minus k e to the n minus k x0 xm plus m minus 1 h sub k. You know, this is really the same as n comma 0 because they are equal means n equals 0, right? Now, and also if n is equal to 0, this only survives when n is equal to 0. So actually this is irrelevant. You can ignore this because it will be 0 if it's non-zero. But the whole thing is going to be 0 anyway. So let me replace this by just k, so it's okay. And then let's take m approaches infinity so that we have infinitely many variables here, right? Then we get an identity like this, k from infinity 0 to infinity minus 1 to, actually it's enough to consider n up to n. So we have an identity like a simple identity like this. And this is actually a well-known identity in the symmetric function theory. So it's probably one of the most elementary results in symmetric functions. So our result here is more general in that sense. It's a kind of something that we can derive this well-known identity from this. All right, that's the example. That's the case that we have this. So in the next few sections, we will consider actually special cases of this. So lambda will still be 0, but this will be something that's specific instead of just indeterminate. Okay, but the idea is quite similar. So let's see what they are. So another special case. Probably this is the simplest non-trivial special case. So we get binomial coefficient. Okay, so in this section we said bk is 1, lambda k is 0. So it's simplest possible, non-trivial. And what happens? If lambda is 0, we already know that mu and k is something generating function for something that goes from 0, 0. Yeah, we already changed the translation, so it's something like that. So it's n minus k comma k, where we go up or horizontal like that. And we put weight here xk, xi's, if this is height I. But now the xi or bi, they are all 1. That means we just count path from here to there, right? So this is number of ways to go from here to here, but that's a binomial coefficient, exactly. So this is n choose k, right? So quite simple. And what about nu? It's a Faber's tiling. Let me write this. Faber's tiling nk, weight prime of t, but we already know that we only have red or black monomials. But we have red. If we have red, the weight is +1. If we have black, the weight is minus p something, but p is always 1, so it's 1. So the weight is always -1 to the n minus k. The weight is always the same, so it's just -1 to the n minus k times number of Faber's tilings. But what is the number of Faber's tilings? We have n squares, but we have to select k squares for red, and then that will determine the remaining squares. So this is what we just saw here is -1. This must be -n to the k, -1 to the n minus k times number of Faber's tilings, which is just n choose k. Okay. So so let me write this as a theorem. If pk equals 1, lambda k equals 0, then we have a very nice identity like this. But again, we get a corollary that these two, if you make a matrix using these and these, they are inverses of each other. This matrix, if you take the inverse, then it's going to be 0 to infinity. Okay, so what that means is what is the matrix? What does the matrix look like? So it is if k is larger than n. So k is here. K the column index is larger than the row index is 0, so it must be a lower triangular, right? And then if k and n are equal, yeah, let me, so it's 0, 0, 1, 1, 1, 0, 2, 0, 2, 1, 2, 2, and they are all 0 like that. But this is, you know, this Pascal triangles is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, goes like that. If you take the inverse of this matrix, it's almost the same. 1, 1, 1, 1 minus, I'm sorry, 2, 1, 1, 3, 3, 1, except we have to put this weight. So the diagonal have the same sign, then the signs alternate. So sign is minus, 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 things like that. So the inverse, we have the nice relation between these two matrices. Pascal, so the matrix, of the Pascal binomial coefficient is invertible, and this inverse also has binomial coefficients. But there's a nice thing about this identity actually. This is related to a very famous principle everybody knows, like the principle of inclusion exclusion. Yeah, and we'll see how this is related to that. So to see the relation, we will define this. Let's say X be a set, any set. A finite set, let's say finite. We want to count something. And let A1 up to AN be the subset of X. We have n subsets of X. So just imagine that, for example, you have this Venn diagram. If you think about it, it looks A1, A2, A3, something like that, if n is equals 3. And we're going to define for a subset of n, define two things. A subscript equal I. This means, but this basically tells you exactly indices in I. So you want to find those that exactly in those A's in this I. So in other words, a set of X's such that X is in some AI, if and only if this is, if and only if I is in I. So this X is in AI for exactly those in this index set I. And similarly, we define greater than equal I. That means X I, what can I say, for all I in there. Or if you want, this is like this. If I is in here, X is in there. Okay? Started if and only if. But actually, if you think about it, this is nothing but A I1 union A I say K if I is I1 dot 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 IK. It's nothing but taking the union of the AIs in the I. Okay, but this is something different. For example, let's say what is A sub 1 equal 1. Only in A, so that must be this part, right? And what about A equal 2, 3? Only in 2 and 4, 3, but not in A, not in A1. So it's this part, like that. But maybe you can. What is A greater than or equal to say 2, 3. This is this part over here, the whole thing. No. It must contain 2, it must contain 3, but that's the only condition. So this part is this. Okay. So of course this must be then intersection. Is the meaning clear? Yeah. Okay. And so, like I said, this can be written in this way. Yeah, I think I made a mistake in the lecture note. You take all the intersection, and if you think about it, so think of this as some kind of property. So we have element, some object here, and A1 is the set of objects having property 1. This is a set of elements having property 2, etc. So then this means set of elements having exactly properties in I. And this is a set of elements that has properties at least those here. So they may be in more, but we don't care. Okay. So what are these? So this is a set of all elements having properties at least I. But if you want to express them as elements with exactly some property, then we can also write this as the union j greater than or equal to I, containing I, A equal j. Is that right? Because if something has property I, at least, then it may have something more. Something more, say j, then it will be exact A equal j. So this all looks like this. By the way, these are all disjoint. A equal I can never be, always empty, unless they are of course equal. Okay. Okay. And because of this, we have, if you consider the cardinality, their cardinalities, this is sum over all j of this. Okay? So just take the cardinalities of both sets. And the question is, can we write this equal thing as a sum of something greater? Okay? Then that's a theorem. This is actually the principle of inclusion exclusion. Principle of inclusion exclusion. Maybe not, we've seen something in a different form, but more or less equivalent. So the theorem is A exact I equals almost the same, except we have to have this sign j minus I. Yeah, you have seen, the idea is really the same. So this, let's just consider what happens in this example, just to get the idea, because I think I introduced new notations like this, maybe confusing, but let's say A1 and A2. And let's say X. What is A empty? This is having no property, so it's outside A1, outside A2, so it's like A1 complement union, intersect A2 complement. Okay, but this, what this is saying is that you consider all possible subsets containing this. That means all subset. So we have empty set empty and minus, and maybe I can just this is plus minus A1 minus A2 plus A1 2, right? But what is this? This means there's no restriction, so it's the whole thing. It's X minus, this is just A1 minus A2 plus A1 intersect A2. So you see, this is exactly the principle of inclusion exclusion in the form that you have seen before. So this is kind of a general version of this form. So I'm not going to give you full details, but let me tell you how to prove this, because the idea is interesting. Yeah, I think if you take any combinatorics course in undergraduate, you will see a proof like this. So proof. We consider every element in our whole set and compute its contribution to left-hand side and right-hand side. How much this element contribute. So here it will contribute either 0 or 1, and here it will contribute, so for each term it will contribute 0, 1, or minus 1. So at the end, the left-hand side must be the contribution of x, every x to the left-hand side, and this must be, the right-hand side must be the sum of the all contributions to the right-hand side. And if you can show that the contribution is exactly the same for every element, then their sum must be the same as well. So that will be the proof. That will be the end of the proof. So to see that, let's say, let's just fix on x, and suppose x is in A equal k. So that means exact property, we just look at exact properties that x has. Then you can uniquely write in this way. So k is the set of properties that x has. So, and we'll consider three cases. Case 1. K is I. Now what is the contribution to the contribution of x to what is the contribution of x to the left-hand side? X is in A equal I, so it will be counted in this set. So the contribution is plus 1. And what about the contribution of x to the right-hand side? Okay, so if x is in this set, it will contribute plus or minus 1. But if x is not here, its contribution will be 0. So we will we consider, let's say, a total contribution. And to consider the total contribution of x to the right-hand side, we only want to look at the j, where j is aj, a greater than j containing x. So this is, by definition of the contribution, this means for those such that x is in A This is what a contribution means. If x is here, we add this. Otherwise, we don't add this. Okay? But what is this? This means x is this. The properties of x is exactly k. How can x be in this set? If j is less than or equal to k as a set containment. So this means j is already greater than or equal to I, that contains I, but it must be contained in k, because then it will be counted here. X will be counted. But otherwise, if j is bigger than k, or it has something that k doesn't have, then x will not be counted there. So it's a yeah. Oh, actually, I was doing the general case. Yeah, but I think it's okay. But this and this, they are equal. So there's only one possible choice for j. J must be I. In that case, this is 0, so it's 1. So the total contribution is 1. Okay? So in that case, we covered. But what about the second case? K contains I, but not equal to I. Now, what is the total contribution? X to the left-hand side. K is not I, so it will be 0. Total contribution. The total contribution is only 1 if I is exactly K. That's the only possible. But what about the total contribution of X to the right-hand side? We already computed this, so we can just work with this. Is sum over I. This is the same, right? But imagine that I already a Venn diagram. Think about the Venn diagram. I, J, K, something like that. I, K fixed. So we only need to look at things that are between outside I and inside K, because these things here are already fixed. So in other words, this is the same thing as we look at only J, let's say J K minus I. I mean, I just ignore this and then just imagine that this part in the ring is J, and that must be contained in this part. Okay, and then this is just J. All right, I'm just collapse the things inside I. And this is non-zero. So, but this means that if the cardinality of J is, say, J from 0 to the total cardinality of K minus I, you have to select among these elements, you just select J elements and minus 1 to the J for the sign. But this is always 0 because this is non-zero. You know, if this is M, this is always 0, is a binomial theorem. Okay, so the contribution is still 0. So that covered. So lastly, K doesn't contain I. Then contribution to left-hand side, again 0. Contribution to right-hand side is also 0 because there's no sum here. J cannot be satisfying both because I is not contained in K. So for every X and every case, the contribution is exactly the same in the right-hand side, left-hand side. And the left-hand side is the sum of all total contributions. Right-hand side is the sum of total contributions. So they must be the same. So that's the proof, basically. So as a special case, if I is empty, as we saw before, we can A equal empty. This means A1 complement, AN complement. And if you write the right-hand side here, the sum is over all subsets, just like we saw over here. All subsets is a J, it contains this. So basically, this is the thing that we see in the usual the principle of inclusion-exclusion form. You consider all possible ways to select two elements, A1, A2, A3, dot, 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 AN minus 1, AN, etc. And at the end, we have minus 1 to the n, A1 intersect AN. So it's the usual principle of inclusion and exclusion. Okay, let me give you an example. There are many examples using principle of inclusion and exclusion. We have already actually seen, but let me use this example, some interesting example. If you haven't seen this, a derangement is a permutation pi, such that it has no fixed point for all k, no fixed point. Yeah, this derangement has just no fixed points. Yeah, maybe you have seen this thing. So it's an interesting example. So imagine that I collected all of your cell phones right now, and then I redistribute this to you randomly. And what is the probability that no one gets his or her own cell phone? Have you seen this problem before? And actually, I think what's more interesting is this. So I am in this semester, I'm teaching two classes, this one and Calculus 2. There are more students in Calculus 2, of course. There are 70 students, and here we have 12. Suppose I do the same thing in the Calculus 2 class, and the same question. Do you think how two answers different? How can those two different? Do you think the chances are much lower here or in the calculus class, or more or less the same? Yeah. Intuitively, the size is big, so maybe the probability can be changed. But the thing is, of course, they are not exactly the same, but they are almost the same. Almost like 30-something%. And we can prove it using this. So, let's see. And this is a simple exercise using the principle of inclusion and exclusion. So the only thing that we need to do is to set the setup. Is the setup. The whole set is the all permutations, and AI is the set of all permutations with a fixed point I as pi I. Okay. Then the derangement. Let's say Dn is the number of derangements. Is of course the set with no properties, exactly no property. Okay. And this we can rewrite this. This is sum over all j minus 1 a greater than or equal to j, right? Actually, the reason why the principle of inclusion and exclusion is useful is that instead of computing the exact elements with exact properties, it's oftentimes easier to compute this, having properties in j, like this. So for example, what is this? If the cardinality of j is, say, j, then what is the cardinality of this? j elements are fixed. Like a j1 goes to j1, j2, k1 goes to k1, k2 goes to k2, kj goes to kj. These are fixed, but the others, they are free. So n minus j elements can be permuted anyway, so n minus j factorial. Okay? So dn, but this only depends on j, the cardinality, right? And the subset of cardinality j is exactly n chooses j, and the sign is -1 to the j, and we have to multiply this cardinality. Okay? Now we can rewrite this, because this is n factorial, j factorial below, and this will cancel. So this is n factorial sum over j from 0 to n, -1 to the j, 1 over j factorial. Okay? So that means if we divide both sides by this here, so that is, n factorial is the cardinality of Sn, equals sum over j from 0 to n. But this one looks familiar to you. If this were the infinity, this is 1 over e. So this is almost 1 over e. Because this sequence, this sum, partial sum, converges to this very quickly. So even if this is only 12, this is very close to this number. And 70 is closer, but almost the same if we just compute them. So this is the probability that no one gets his or her own cell phone. If I randomly distribute them, it's going to be 1 over e. So it's, I don't know exactly, but it's 0.30 something, yeah. Okay, and there is an interesting observation that we can make here. So here, look at this. Something nice happened in order to enumerate things. This cardinality in this example depends only on the cardinality of j. It doesn't matter what elements j has. As long as j has like 3 elements, they all have the same number. The cardinality will be the same. Imagine this situation. Suppose a greater than equal to j and a greater than equal to j. Let's use I. Yeah, it doesn't really matter, but depend only on the cardinality of I, just like we in the example. Then we can write if the cardinality of I is k, we can write this is say bk equal ak, because it depends only on the cardinalities. We can write in this way. Okay. Then what is okay? How can we rewrite? Where is it? Right. Let me just copy this. Yeah, so that we can just look at them side by side. Then how can we rewrite these two? Then this, the first one, let's say I has cardinality k, so bk equals sum over all j containing I, right? But I it already has k elements, so except the remaining we may have at most n minus k more element. So j goes from, or maybe I can just go k to n, let's say. Then maybe I can just explain this. Okay, we can rewrite this in this form. yeah, if the cardinality of this is J must be from K to N. But this is the number of possible J, because we have N minus K, because the elements in I, the K elements are already fixed. Among the N minus K, we have to select K minus J, so that eventually we get J element. And this is always A sub J. And the second one can be rewritten in a similar way. Yeah, like that. And for some reason, just to make things nicer, we define A prime just to be kind of complement. Then I'm going to skip the details. This is just a simple computation. You can do it yourself. Then we can rewrite these as follows. bk prime equals, in a nice way, j prime, ak prime, k minus j, kj, b j prime. So this is equivalent to this. It's all just a simple change of indices and things like that. And if you look at them carefully, it looks like the identity using a matrix. We can write in this way: bk n prime equals. If you write this for all k from 0 to n, we can write this as a matrix identity: ij from 0 to n, a 0 prime, a n prime, and also a 0 prime, a n prime, minus 1 to the I minus j, ij from 0 to n, b 0 prime, b n prime. So this is really equivalent to this. But b's and a primes, they can be arbitrary numbers. We can just assign by, we can choose a's and x so that we can make them arbitrary. So in other words, this is always true for any choices of b's and a's. But that means this must be an inverse matrix of this. Okay? ij inverse. But you now remember this is exactly, I think I made a typo, ij. But this is exactly the identity that we saw before for the simplest non-trivial case of our duality. So it also contains this some kind of principle of inclusion and exclusion. Okay. All right. So yeah, I'll stop here, and we will see 2 more examples the next lecture.